I am Priyanka Kurgund from MTech third semester Power System Engineering. Now I am giving a seminar on parallel systems. These are the contents of my seminar, that is unrepairable components in parallel, repairable components in parallel, and some examples. Unrepairable components in parallel system. The block diagram consisting of two components connected in a parallel as shown in the figure. Assume that the two components are independent. Therefore, to have the system fail, the both components must fail simultaneously. Thus, the system unreliability is given as Q system is equals to probability function P of event 1 and event 2, where lambda 1 and lambda 2 are failure rates of component 1 and 2, where small r and small r1 and r2 are repair rates of component 1 and 2. Q1 and Q2 are unavailability of the component 1 and 2. Capital R1 and R2 are reliability of the component 1 and 2. Since it is assumed that the components are independent, so that the equation can be given as Q system is equals to probability function P of event 1 into probability function P of event 2, that is equation 11.87, which can also be written as Q system is equals to pi 1 I tends to 1 to 2 into 1 minus Ri, where Ri is the reliability component of the I, where Ei bar is the event of the component I fails and Qi is the unreliability of the component I, and Q system is the unreliability of the system. Then the system reliability is given by the complementary probability as R system is equals to 1 minus Q system. By substituting the 11.88 in this equation, that is R system is equals to 1 minus pi I tends to 1 to 2 into 1 minus Ri. This is for the 2-unit redundant system. To generalize this concept, consider a parallel system with the m independent compounds as shown in the figure, that is in the next slide. Therefore, the system unreliability can be expressed as Q system is equals to probability function of event E1, E2, E3, so on for Em. Since it is a m components are independent, this unreliability function Q system can be given as probability of event E1 into probability function of event E2 into probability function of event E3, so on to the probability function of Em, which also can be given as Q system is equals to Q1 into Q2 into Q3 into so on to Qm. Therefore, to find the system reliability, that is R system is equals to 1 minus Q system, that can be given as 1 minus pi I tends to 1 to m into Qi. This is the block diagram of a parallel system with the m components connected to that, which can be given with the equation of R system is equals to 1 minus pi I tends to 1 to m into 1 minus Ri. As we can see in the figure that the given component reliability of the margin gain in the system reliability due to the addition of the parallel paths decreases rapidly. Thus, the greatest gain in the system reliability occurs when the second path is added to the single path. By observing this figure, we can come to know that the marginal gain of the system reliability is getting decreased by adding the parallel paths. As the parallel path increases, the marginal gain goes on decreases. Where the reliability of a parallel system is not a simple exponential, but it is a sum of exponential. Therefore, the system reliability of two components connected to the parallel system can be given as this equation, that is R system of t is equals to 1 minus of 1 minus e raised to minus lambda 1 into t into 1 minus e raised to minus lambda 2 into t. That can further be given as that equation 11.94, where the lambda 1 is the failure rate of the component 1 and lambda 2 is the failure rate of the component 2. Unrepairable components in the parallel system. Consider a parallel system with the two components as shown in the figure earlier. Assume that the components are independent and repairable. Therefore, the unavailability of the system can be expressed as U system is equals to U1 into U2, where the U can be unavailability of the system that can be expressed as MTTR divided by MTTR plus MTTBF, where MTTR is the mean time to repair, which is denoted by R bar. MTBF is a mean time between the repair, that is denoted by M bar, where U1 and U2 are unavailability of the component 1 and 2. From this, we can find U1, where U1 is equals to 1 minus A1. That A1 is the availability of the system that can be given as MTBF divided by MTTR plus MTBF. By this, we can get the formula, that is 11.96, that is lambda 1 into lambda 1 into R1 bar divided by 1 plus lambda 1 into R1 bar. Similarly, the unavailability of a component 2 can be given as U2 is equals to 1 minus A2, which can be further given as lambda 2 into R2 bar divided by 1 plus lambda 2 into R2 bar. By substituting the equation U1 and U2 in U, we can get this equation number 11.98. However, the average frequency of the system failure is given as F bar system is equals to U2 into F1 bar plus U1 into F2 bar, where F bar system is the average frequency of the system failure, where F1 and F2 are the failure rates of two components, frequency failure rates of the two components, where U1 and U2 are the unavailability of the component U1 and U2. Since F1 is equals to lambda 1 divided by 1 plus lambda 1 into R1 bar and F2 is lambda 2 divided by 1 plus lambda 2 into R2 bar. By substituting the equation F1, F2, U1 and U2, we can get a F bar system as given as a equation 11.102. From using the equation 11.50, that is U is equals to R bar by T bar, the system unavailability can be expressed as U system is equals to R bar system by T bar system, which can further changed into U system is equals to R bar system into F system, because F bar system is equals to 1 by T bar system. So that R bar system is equals to U system divided by F bar system. Therefore, by substituting the system unavailability by the system failure frequency, we can get R bar system is equals to R1 bar into R2 bar divided by R1 bar plus R2 bar. Further, which can be given as 1 by R bar system is equals to 1 by R bar plus 1 by R2. Similarly, this from the equation 11.51, we can give as a U is equals to R bar divided by R bar plus M bar, where the system unavailability can be expressed as U system is equals to R bar system divided by R bar system plus M bar system, from which we can get a M bar system that is equals to R bar system into 1 minus U system divided by U system. By substituting the equation system unavailability and average repair time in a M bar system, which can be expressed as average time to the failure, that is M bar system is equals to 1 plus lambda 1 into R bar 1 plus lambda 2 into R bar 2 divided by lambda 1 into lambda 2 of R1 bar plus R2 bar. The failure rate of the parallel system can be given as lambda bar system, which is inversely proportional to the average time of failure, that is 1 by M bar system, or which can be also expressed as the equation 11.112. When more than two identical units are connected in parallel, or when the system is not purely redundant, that is parallel, the probabilities of the states or modes of the system can be calculated by using the binomial distribution or a conditional probabilities. Example, as shown in the figure, consider that a 4-mile long distribution express feeder, which is used to provide electric energy to the load center located in the downtown area of the coast city from the Coast River substation. Approximately 1 mile of a feeder has been built underground due to the intrinsic consideration in the vicinity of the downtown area, while the rest of the feeder is overhead feeder, that is 3 miles as shown in the figure. The underground feeder has two termination points. On average, two faults per circuit mile for the overhead sections and one fault per circuit mile for the underground section of the feeder have been recorded for the last 10 years as shown in the figure. The annual cable termination fault, that is rate, is given by 0.3% per cable termination. Further, based on past experience, it is known that on average the repair times for the overhead sections, underground sections, and each cable termination can be given as 328 3 hours. That is 3 hours for a overhead section, 28 hours for a underground section, 3 hours for a cable termination. That is the average repair time. Using this information, they have told to determine the total annual fault rate of the feeder, average annual fault restoration time of the feeder in hours, and unavailability of the feeder and availability of the feeder. Firstly, they have said to calculate the total annual fault rate of the feeder. which can be given as the equation below. That is, delta FDR is equals to summation of I is equals to 1 tends to 3 of lambda I, where I is equals to 1 to 3 is considered as the three sections, that is overhead section, underground section and cable termination, where lambda OH is the total annual fault rate of the overhead section of the feeder and lambda UG is the total annual fault rate of the underground section of the feeder and lambda CT is the total annual fault rate of the cable termination. Therefore, lambda FDR is equals to 3 into 2 by 10, where the 3 is the total area, that is 3 miles of overhead section, and 2 is the fault per circuit mile considered for the overhead section, and 10 years is the duration of the faults that has been recorded. Similarly, for the underground section, 1 is the area considered, that is 1 mile for the underground section, and 1 by 10, which is the 1 fault per circuit miles and 10 years, plus 2 into, that is 0.3%, which has been given in the question, that the cable termination faults rate. From this we can get faults per year, that is 0.706 faults per year. To find the average fault restoration time of the feeder per fault is given as R bar FDR, that is equals to summation of I is equals to 1 times to 3 RI bar, where ROH is the average repair time of the overhead section of the feeder, R bar UG is the average repair time of an underground section of the feeder, and RCTC is the average repair time per cable termination, which can be solved as R bar FDR is equals to 3 plus 28 plus 2 into 3, where the first 3 is 3 hours given for the overhead section and 28 hours is repair time given for the underground section, and next 3 hours is overhead. Next 3 hours is repair time given for the cable termination. By using this data, we have found out that RD bar is equals to 37 hours. The average annual fault restoration of the time of feeder is given as this above equation. By substituting the values that are given in our data, we can find that FDR bar is equals to 6.54 hours. Next is unavailability of the feeder. That firstly we have derived that U is equals to R bar divided by R bar plus M bar. From using that formula, we can find that unavailability of the feeder. That is given equation UFDR is equals to R bar FDR divided by R bar FDR plus M FDR, where MFDR is the annual mean time to failure, which can be known by using this 8706 minus R bar FDR, where 8760 is the mean time to failure for 1 year, that is 365 days into 24 hours, that is 8760 minus the RFDR which has been calculated above, that is 6.54, we get 8753.46 hour per year. By substituting the values in the UFDR, we can get a 0.07 percentage of unavailability of the feeder. Next is availability of the feeder, which can be found by using that unavailability of the system. We know that the availability can be given as 1 minus unavailability of the feeder, that is delta FDR is equals to 1 minus UFDR, that is 1 minus 0.07%, we get 99.93% as the availability of the feeder. Example 11.3. Assume that the primary main feeder as shown in the figure, which is in the next slide, where the manually sectionalized and that presently only the first three feeder section exist and service customers, that is A, B, C are the three sections. The annual average fault rates for the primary main feeder and laterals are given as 0.08 for the main primary and zero point 0.2 for a lateral, that is fault per circuit miles respectively. The average repair time for each primary main section and for the each primary laterals are given as 3.5 and 1.5 hours respectively. The average time for the manual sectionalization of the each feeder section is 0.75 hours. Assume that at the time having one of the feeder section is in fault, the other section are sectionalized manually as long as they are not in the mainstream of the fault current, that is, not in between the faulted section and the circuit breaker. Otherwise, they have to be repaired also. Based on this given information, prepare an interruption analysis study for the first constituency only. They have asked to prepare a interruption analysis study for only first contingency analysis. That is, IS ignore the possibilities of the simultaneous outages and determine the following. First to determine is the total annual sustained interruption rates for the customer A, B, C and the average annual repair times, that is down times for the customer A, B and C. This is the area that has been considered for the sectionalization of the system. That are sections are section 1, section 2, section 3, section 4, section 5 as shown in this figure. But they have mentioned that to consider the sections which are connected to the customers A, B and C. By keeping this in consideration, the total annual sustained interruption rates to the customer A, B, C are calculated by using a formula as given below. That is, lambda A is equals to summation I tends to 1 to 4 into lambda I, where lambda I is three sections, that is lambda section 1 plus section 2 plus section 3 and plus lateral of A. That by substituting the values we get faults per year is 0.64 for a area of customer A. Similarly, for remaining customers B and C, they have calculated fault per year as 0.54. For the next to calculate the average annual repair time, this that downtime for the customer A is given as the equation RA bar is equals to lambda section 1 into R bar fault plus lambda section 2 into R bar MS plus lambda section 3 into RMS bar plus lambda lateral A into R bar lateral fault whole divided by lambda A, that lambda A has been already calculated in the previous section, where lambda A bar is the average repair time for the customer A. Lambda section is the total fault rate of the feeders per year. Lambda bar fault is the average repair time for the faulted primary main section. R bar lateral fault is the average repair time for the faulted primary lateral, where the R bar ms is the average time for the manual sexualization per sections, and lambda lateral A is the total fault rate for the lateral A per year. By substituting all values in R bar A, we get the repair time as 1.56 hours for the customer A. To calculate for the remaining customers B and C, same formula has been used, that is shown in the next slide. Similarly, for customer B, they have calculated the repair time, that is R bar B, by substituting the values in the R bar B equation, that is 1.98 hours. And for customer C, they have calculated the repair time by using the equation R bar C. By substituting the values, they have calculated, that is 2.39 hours for the customer C. Thank you for your patience hearing.